Gravitation. Universal law of gravitation. Every object in the universe attracts every other object with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. The force is along the line joining the centers of two objects. Object A with mass m, object B with mass m, small m. The force between them is directly proportional to the product of their masses, that is m into m, and inversely proportional to the square of the distance between them. So the force acts along the line of force. This is the line joining the two centers of the objects. The force acts on this line. Let two objects A and B of masses m and n lie at a distance d from each other as shown in the above figure. Let the force of attraction between two objects be F. According to the universal law of gravitation, the force between two objects is directly proportional to the product of their masses, that is, F is proportional to m into m, and the force between two objects is inversely proportional to the square of the distance between them, that is, F is proportional to 1 by d square. Combining the above equations, F is proportional to m into m divided by d square, or F is equal to g into m divided by d square, where g is the constant of proportionality and is called the universal gravitation constant. By multiplying crosswise, this will become F into d square. F into d square is equal to g m into m, or g is equal to f d square divided by m into m. The SI unit of g can be obtained by substituting the units of force, distance and mass in this equation as Newton meter square per kg square. The value of g was found out by Henry Cavendish by using a sensitive balance. The accepted value of g is 6.673 into 10 to the power of minus 11 Newton meter square per kg square. So in this example, the mass of the earth is 6 into 10 to the power of 24 kg, and that of the moon is 7.4 into 10 to the power of 22 kg. If the distance between the earth and the moon is 3.84 into 10 to the power of 5 kilometers, calculate the force exerted by the earth on the moon. Take g is equal to 6.7 into 10 to the power of minus 11 Newton meter square per kg square. So before solving, we need to convert this kilometer into meter, because we have the thing Newton meters per second per kg square. We need to convert this. So after converting, substitute all the values of g, mass of the earth, mass of the moon, and the distance between them, and calculate. Mass of the earth is given by m is equal to 6 into 10 to the power of 24 kg. Mass of the moon m is equal to 7.4 into 10 to the power of 22 kg. Distance between the earth and the moon is d is equal to 3.84 into 10 to the power of 5 kilometers. To convert kilometer into meters, multiply the whole thing by 1000, it will become meters. Then 3.84 into 10 to the power of 8 meters, the distance has become like that. So that g, they were given 6.7 into 10 to the power of minus 11 Newton meter square kg per kg square. Substitute all the values here. In this equation, F is equal to gm into m divided by d square. After calculations, we got it. The force has become 2.02 into 10 to the power of 20 newtons. Thus, the force exerted by the earth on the moon is 2.02 into 10 to the power of 20 newtons. Free fall. Let us try to understand the meaning of free fall by performing this activity. Take a stone, throw it upwards, it reaches a certain height and then it starts falling down. We have learned that the earth attracts objects towards it. This is due to the gravitational force. Whenever objects fall towards the earth under this force alone, we say that the objects are in free fall. Is there any change in the velocity of falling objects? While falling, there is no change in the direction of motion of the objects, but due to the earth's attraction, there will be a change in the magnitude of the velocity. Any change in the velocity involves acceleration. Whenever an object falls towards the earth, an acceleration is involved. This acceleration is due to the earth's gravitational force. Therefore, this acceleration is called the acceleration due to gravitational force of the earth, or acceleration due to gravity. It is denoted by g. The unit of g is the same as that of acceleration, that is meter per second square. We know from the second law of motion that force is the product of mass and acceleration, F is equal to ma. Let the mass of the stone in the activity be m. We already know that there is acceleration involved in falling objects due to the gravitational force and is denoted by g. Therefore, the magnitude of the gravitational force F will be equal to the product of mass and acceleration due to the gravitational force, that is F is equal to mg. And we also know that F is equal to g m into m by d square. So when you substitute for F here, mg will be equal to g into m by d square. This m and this will get cancelled, or g is equal to g into m divided by d square, where m is the mass of the earth and d is the distance between the object and the earth. Let the object be on or near the surface of the earth. The distance will be equal to or the radius of the earth. Thus, for the objects or near the surface of the earth, mg is equal to g into m divided by the r square, where r is the radius of the earth. Then g is equal to g into m by r square. The earth is not a perfect sphere. As the radius of the earth increases from the poles to the equator, the value of g becomes greater at the poles than at the equator, because as the radius increases, the gravity becomes less, because the r is in the denominator. The earth is not a perfect sphere. As the radius of the earth increases from the poles to the equator, the value of g becomes greater at the poles than at the equator. To calculate the value of g, we should put the values of g, m and r in equation g is equal to gm divided by r square. Namely, universal gravitation constant g is equal to 6.7 into 10 to the power of minus 11 Newton meter square per kg square. Mass of the earth m is equal to 6 into 10 to the power of 24 kg, and the radius of the earth or is equal to 6.4 into 10 to the power of 6 meters. Substitute all values of g, m and r square after substituting all the values here, and after simplification we got it g is equal to 9.8 meter per second square. Thus the value of acceleration due to gravity of the earth, g is equal to 9.8 meter per second square. In this problem, a car falls off a ledge and drops to the ground in 0.5 seconds. That is g equal to 10 meter per second square for simplifying the calculations. What is its speed on striking the ground? What is its average speed during the 0.5 seconds? How high is the ledge from the ground? See here, the car is falling from the ledge and drops down. So when it is falling, the initial velocity was 0 and it was falling through 5 seconds, and it has fallen from the bridge, from the ledge it has traveled the distance for 5 seconds. We need to find out the speed. The speed can be found out using v is equal to u plus at. The u is 0, it is due to gravity that they have given 10 meters per second square, time as 0.5 seconds. The average speed can be found out using the formula average speed is equal to u plus v divided by 2, where u is 0, v we have found out in the previous thing. Then we go to the distance traveled. For the distance traveled we can use the formula is equal to ut plus half at square. So in that u is 0, then use of a into t square, where a is equal to, that is acceleration due to gravity, that is 10 meters per second square, t is 0.5 whole square, that is 0.25. When you calculate, you get all the answers. The speed we got 5 meters per second using the v is equal to u plus at, where u is 0. Here average velocity we got as 2.5 meters per second, where initial velocity is 0. Here distance traveled also, where s is equal to ut plus half at square, where u is 0. We got it after finding calculations 1.5 meters the car traveled. An object is thrown vertically upwards and rises to a height of 10 meters. Calculate the velocity with which the object was thrown upwards and the time taken by the object to reach the highest point. See, when you throw the stone upwards, at some point the final velocity becomes 0, and that has traveled for 10 meters. That is the distance traveled, s is equal to 10 meters. See, while throwing up, when the stone is thrown up, it is moving against the gravity. Then we have to take the acceleration of that object as minus 9.8 meters per second square. When it is acceleration due to gravity, we have to take 9.8 meters per second square. They have asked us to find out the velocity with which the object was thrown upwards, that is the initial velocity we need to find out. We know that the final velocity is 0. Using the formula v square is equal to u square plus 2as, the v will become 0. U square, u we need to find out 2. A, it is moving up, that's why it is taken as minus, it is against gravity, minus 9.8 meter per second square. Distance traveled is 10 meters. After calculations you got it, initial velocity is equal to 14 meters per second. Now they are asking how much time it has taken to travel. For the object to reach the highest point, we can use this formula v is equal to u plus at. There is a time here. We know that final velocity is 0. Just now we found out the u is equal to 14 meters per second. A, it is minus 9.8. So then after calculations we got it, time is equal to 1.43 seconds. The time taken to reach the highest point is 1.43 seconds. Let us see what mass. We have learned in the previous chapter that the mass of an object is the measure of its inertia. We have also learned that greater the mass, the greater is the inertia. It remains the same whether the object is on the earth or on the moon or even in outer space. Thus, the mass of an object is constant and does not change from place to place. Weight. We know that the earth attracts every object with a certain force, and this force depends on the mass m of the object and the acceleration due to gravity g. The weight of an object is the force with which it is attracted towards the earth. We know that F is equal to ma, that is F is equal to mg. The force of attraction of the earth on the object is known as the weight of the object. It is denoted by W. Substituting the same in the equation, above equation, the force is nothing but a weight that is equal to m into g. The force of attraction of the earth on the object is known as the weight of the object. It is denoted by W. Therefore, W is equal to m into g. W is equal to m into g, as the weight of an object is the force with which it is attracted towards the earth. The SI unit of weight is same as that of the force, that is Newton. The weight is a force acting vertically downwards. It has both magnitude and direction. We have learned that the value of g is constant at a given place. Therefore, at a given place, the weight of an object is directly proportional to the mass, say m, of the object. That is, W is proportional to weight is proportional to the mass. It is due to this reason that at a given place we can use the weight of an object as a measure of its mass, because we have taken gravity as constant. The mass of an object remains the same everywhere, that is, on the earth and on any planet, whereas its weight depends on its location, because g depends on location. Weight of an object on the moon. We have learned that the weight of an object on the earth is the force with which the earth attracts the object. In the same way, the weight of an object on the moon is the force with which the moon attracts that object. The mass of the moon is less than that of the earth. Due to this, the moon exerts lesser force of attraction on objects. Let the mass of an object be m. Let its weight on the moon be W with subscription m. Let the mass of the moon be m, and its radius be rm. All these things are related to the moon. By applying the universal law of gravitation, the weight of the object on the moon will be Wm is equal to gmm into m divided by r square, where mm is the mass of the moon, rm is the radius of the moon, m is the mass of an object on moon. So this is the weight of the moon. Let the weight of the same object where we weighed in the moon on the earth be We. The mass of the earth is m and its radius is r. Here earth's mass is 5.98 into 10 to the power of 24. The radius of earth is 6.37 into 10 to the power of 6. The mass of moon is 7.36 into 10 to the power of 22. The radius of moon is 1.74 into 10 to the power of 6. Let us substitute all the values in the equation. W is equal to g into m divided by r square for the moon as well as for the earth. We is equal to g into m divided by r square. Substituting the values which is given in the table. So Wm is equal to g into 7.36, that is the mass of the moon, into 10 to the power of 2 kg per kg into meter, divided by the radius of the moon, which is 1.74 into 10 to the power of 6, the whole square. So Wm is the object's weight on the moon, We is the object's weight on the earth. This is the object's weight on the moon, We is the object's weight on the earth. So after calculation we got it, Wm is equal to 2.431 into 10 to the power of 8, g into m. See, the object's weight on the earth is 1.474 into 10 to the power of 11 g into m. Dividing these two, this divided by this, wm by w, the g, mm get cancelled. Then 2.431 into 10 to the power of 8 divided by 1.474 in 10 to the power of 11. That has become Wm divided by We is equal to 1.165, that is equal to 1 by 6. The weight of an object on the moon, that is Wm. Weight of the object on the earth, that is W, is equal to 1 by 6. That is, the weight of the object on the moon is equal to 1/6 of its weight on the earth. That is, if it is the weight of the object is 6 kgs on the moon, it's going to be 1 kg on the earth. Let us see this problem. Mass of an object is 10 kg. What is the weight on the earth? Mass, they have given us 10 kgs. Acceleration due to gravity is 9.8. W is weight is equal to mass into gravity. That is, W is equal to 10 into 9.8 meters per second square. That has become 98 newtons. That is, the weight of the object is 98 newtons. An object weighs 10 newtons when measured on the surface of the earth. What would be its weight when measured on the surface of the moon? We have the formula for that. We know the weight of the object on the moon is equal to 1/6 its weight on the earth. That is, Wm is equal to Wu by 6, that is 10 by 6, that is 1.67 newtons. Thus, the weight of the object on the surface of the moon would be 1.67 newtons, which was 10 newtons on the earth. The thrust and pressure. Have you ever wondered why a camel can run in a desert easily? Why an army tank weighing more than 1,000 tons rests on a continuous chain? Why a truck or a motor bus has much wider tires? Why cutting tools have sharp edges? In order to address these questions and to understand the phenomena involved, it helps to introduce the concepts on the bulletin board as shown in the figure. To do this task, you will have to press drawing pins with your thumb. As you apply a force on the surface area of the head of the pin, this force is directed perpendicular to the surface area of the board. This force acts on a smaller area at the tip of the pin. Now the second situation, where you stand on loose sand, your feet go deep into the sand. Now lie down on the sand. You will find that your body will not go that deep in the sand. In both the cases, the force exerted on the sand is the weight of your body. You have learned that the weight is the force acting vertically downwards. Here the force is acting perpendicular to the surface of the sand. The force acting on an object perpendicular to the surface is called thrust. The force acting on an object perpendicular to the surface is called thrust. When you stand on the loose sand, the force, that is the weight of your body, is acting on an area equal to the area of your feet. When you lie down, the same force acts on an area equal to the contact area of your whole body, which is larger than the area of your feet. Thus, the effects of forces of the same magnitude on different areas are different. In the above cases, thrust is the same, but effects are different. Therefore, the effect of thrust depends on the area on which it acts. The effect of thrust depends on the area on which it acts. The effect of thrust on sand is larger while standing than while lying. The thrust on unit area is called as pressure. The thrust on unit area is called pressure. Thus, pressure equal to thrust divided by area. Substituting the SI unit of thrust and area in this above equation, we get the SI unit of pressure as Newton per meter square. In honor of a scientist, Blaise Pascal, the SI unit of pressure is called Pascal, denoted as PA. Let us consider a numerical example to understand the effects of thrust acting on different areas. This example, a block of wood is kept on a tabletop. The mass of a wooden block is 5 kgs and its dimensions are 40 centimeters into 20 centimeters into 10 centimeters. Find the pressure exerted by the wooden block on the table top if it is made to lie on the tabletop with its sides dimensions in A 20 centimeters, 10 centimeters, that is the surface lying on the table, and second case 40 centimeters and 20 centimeters. This is the question they are asking. When you keep the surface of the block 20 centimeter surface, if you keep on the block, what is the pressure exerted? When you reverse this and keep the surface, contact surface on the table is 20 centimeters, 40 centimeters dimensions, what is the pressure exerted on the table? The mass of the wooden box they given as 5 kgs, the dimension as 40 centimeters into 20 centimeters into 10 centimeters. Here the weight of the wooden block applies a thrust on the tabletop, that is thrust is equal to F is equal to MA, where M is equal to 5 kgs, M is 9.8 meters per second square, that is due to gravity. The thrust F is equal to 49 newtons. Area of a side is equal to length into breadth. In the first case, the length which is lying on the table, which is making contact with the table, length is 20 centimeters, the breadth is 10 centimeters, that has become 200 centimeters square. We need to convert that into meters square. When there is centimeter, divide with 100 into 100. When you divide with 100 into 100, this will get 0.02 meters square. We know that the pressure is equal to thrust divided by area. Pressure is equal to, we found out that the thrust is equal to 49 newtons divided by area is, in the first case where the area of the sides 20 centimeters, 10 centimeters lying on the table, that has become 0.02 meters square. The pressure exerted on the table 2450 Newton per meter square. When the block lies on its side dimensions 40 and 20 centimeter, which is the longer side, it exerts the same thrust. So the weight is same, thrust is same. Area is equal to length into breadth. The area is increased here, 40 into 20 centimeter, that 800 centimeters square. Divide this 800 by 100 into 100 to convert it into meters. That has become 0.08 meters square. So we know that pressure is equal to thrust by area. Pressure is equal to 49 divided by the new area with larger area, 0.08 meters square. The pressure exerted on the table is 612.5 Newton meter square. As the area increases, the pressure is going to be less. The pressure exerted by the side 20 centimeters, 10 centimeters is 2450 Newton meter square, and by the side 40 into 20 centimeters, it is 612.5 Newton per meter square. The pressure in fluids, all liquids and gases are fluids. A solid exerts pressure on a surface due to its weight. Similarly, fluids have weight and they also exert pressure on the base and walls of the container in which they are enclosed. Pressure exerted in any confined mass of fluid is transmitted undiminished in all directions. Buoyancy. Have you ever had a swim in a pool and felt lighter? Have you ever drawn water from a well and felt that the bucket of water is heavier when it is out of the water? Have you ever wondered why a ship made of iron and steel do not sink in sea water, but while the same amount of iron and steel in the form of sheet would sink? These questions can be answered by taking buoyancy in consideration. Let us understand the meaning of buoyancy by doing an activity. Take an empty plastic bottle, close the mouth of the bottle with an airtight stopper, put it in a bucket filled with water. You see that the bottle floats. Push the bottle into the water. You feel an upward push. Try to push it further down. You will find it difficult to push deeper and deeper. This indicates that water exerts a force on the bottle in the upward direction. The upward force exerted by the water goes on increasing as the bottle is pushed deeper till it is completely immersed. Now release the bottle. It bounces back to the surface. Does the force due to the gravitational attraction of the earth act on this bottle? If so, why doesn't the bottle stay immersed in water after it is released? How can you immerse the bottle in water? The force due to the gravitational attraction of the earth acts on the bottle in the downward direction. So the bottle is pulled downwards, but the water exerts an upward force on the bottle. As the bottle is pushed upwards, we have learned that the weight of the object is the force due to the gravitational attraction of the earth. When the bottle is immersed, the upward force exerted by the water on the bottle is greater than its weight. Therefore, it rises up when released. To keep the bottle completely immersed, the upward force on the bottle due to water must be balanced. This can be achieved by an extreme externally applied force acting downwards. This force must at least be equal to the difference between the upward force and the weight of the bottle. The upward force exerted by the water on the bottle is known as upthrust or buoyant force. In fact, all objects experience a force of buoyancy when they are immersed in a fluid. The magnitude of this buoyant force depends on the density of the fluid. Why objects float or sink when placed on the surface of water? Let us do the following activities to arrive at an answer for the above question. Take a beaker filled with water, take an iron nail and place it on the surface of the water. Observe what happens. The nail sinks. The force due to the gravitational attraction of the earth on the iron nail pulls it downwards. There is an upthrust of water on the nail which pushes it upwards, but the downward force acting on the nail is greater than the upthrust of water on the nail, so it sinks. See here, the nail has sunk. The nail has sunk into this because downward force is more than the upward thrust. Take a beaker filled with water, take a piece of cork and an iron nail of equal mass, place them on the surface of water, observe what happens. See, the nail is sunk, the cork is floating on the water of same weight. The cork floats while the nail sinks. This happens because of the difference in their densities. The density of a substance is defined as mass per unit volume. The density of the cork is less than the density of water. This means that the upthrust of water on the cork is greater than the weight of the cork, so it floats. The density of an iron nail is more than the density of water. This means that the upthrust of water on the iron nail is less than the weight of the nail, so it sinks. Therefore, objects of density less than that of liquid float on the liquid. The objects of density greater than that of a liquid sink in the liquid. Archimedes Principle. Archimedes Principle states that when a body is immersed fully or partially in a fluid, it experiences an upward force that is equal to the weight of the fluid displaced by it. The Archimedes Principle states as when a body is immersed fully or partially in a fluid, it experiences an upward force that is equal to the weight of the fluid displaced by it. Archimedes Principle has many applications. It is used in designing ships and submarines, lactometers, which are used to determine the purity of a sample of milk, and hydrometers used for determining density of liquids are based on this principle. Relative density. As you know, the density of a substance is defined as mass of a unit volume. The unit of density is kilogram per meter cube. The density of a given substance under specified conditions remains the same. Therefore, the density of a substance is one of its characteristic properties. It is different for different substances. For example, the density of gold is 19,300 kg per meter cube, while that of water is 1000 kg per meter cube. See the difference? Here 1000 kilograms per meter cube, here it is almost 19 times 19,300 kilograms per meter cube. The density of a given sample of a substance can help us to determine its purity. It is often convenient to express density of a substance in comparison with that of water. The relative density of a substance is the ratio of its density to that of water. Relative density is equal to density of a substance divided by density of water. So we are comparing the density of a water with the density of a substance with the water. That is relative comparison. So relative density of is equal to density of a substance divided by density of water. Since the relative density is a ratio, then similar quantities, it has no unit. Relative density does not have the unit. Relative density of silver is 10.8. They have given relative density of silver as 10.8. The density of water is 10 cube, that is 1000 kg per meter cube. What is the density of silver in SI unit? They have given the relative density, they have given the density of water, then we need to find out the density of silver. Relative density is given by 10.8. Relative density formula, we have density of a silver divided by density of water. Therefore, density of silver is equal to relative density into density of water, that is 10.8 into 10 to the power of 3 kg per meter cube.